नमस्कार, मैं आनंद कुमार खत्री, एसोसिएट प्रोफेसर ऑफ जूलॉजी, गवर्नमेंट डूंगर कॉलेज, बीकानेर। आज के हमारे लेक्चर का विषय है हाइड्रोस्फीयर। जैसा कि हमने पूर्व में भी हाइड्रोस्फीयर से रिलेटेड बात की है, इसी से रिलेटेड इसका पार्ट 3। वाटर साइकिल, जनरल नेचर ऑफ द साइकिल। द प्रेजेंट डे वाटर साइकिल एट अर्थ सरफेस इज मेड अप ऑफ several parts. Some 4,96,000 cubic kilometer of water evaporates from the land and ocean surface annually, remaining for about 10 days in the atmosphere before falling as rain or snow. The amount of solar radiation necessary to evaporate this water is half of the total solar radiation received at Earth's surface. About 1/3 of precipitation falling on land runs off to the ocean primarily in rivers, while direct groundwater discharge to the ocean accounts for only about 0.6% of the total discharge. A small amount of precipitation is temporarily stored in the water of rivers and lakes. The remaining precipitation over land, 73,000 cubic kilometer per year, returns to the atmosphere by evaporation. Over the ocean, evaporation exceeds precipitation, and the net difference represents transport of water vapor over land, where it precipitates as rain or snow and returns to the ocean as river runoff and direct groundwater discharge. ये इसमें सरफेस हाइड्रोलॉजिक साइकिल दिखाया गया है. The various reservoirs in the water cycle have different water resistance time. Residence time is defined as the amount of water in a reservoir divided by either the rate of addition of water to the reservoir or the rate of loss from it. The ocean have a water residence time to 3,000 to 3,230 years. And this long residence time reflects the large amount of water in the ocean. In the atmosphere, the residence time of water vapor relative to total evaporation is only about 10 days. Lakes, river ice and groundwater have residence time lying between these two extremes and are highly variable. There is considerable variations in evaporation and precipitations over the globe. In order for precipitations to occur, there must be sufficient atmospheric water vapor and enough rising air to carry the vapor to an altitude where it can condense and precipitate. Precipitations and evaporation vary with latitude and their relation to the global winds belts. The trade winds, for example, are initially cool, but they warm up as they blow towards the equator. These kind winds pick up moisture from the ocean, increasing ocean surface salinity and causing seawater of the surface to sink. When the trade winds reach the equator, they rise and the water vapor in them condenses and forms clouds. Net precipitation is high near the equator and also in the belts of the prevailing westerlies where there is frequent storms activities. Evaporation exceeds precipitation in the subtropics where the air is stable and near the poles where the air is both stable and has a low water vapor content because of the cold. The Greenland ice sheet and the Antarctic ice sheet formed because the very low evaporation rates at the poles resulted in precipitation exceeding evaporation in these local regions. process involved in the cycle. The water cycle consists of various complicated processes that move water throughout the different reservoirs on the planet. The major processes involved are precipitation, evaporation, interception, transpiration, infiltration, percolation, retention, detention, overland flow, through flow, and runoff. Water vapor and precipitation. As noted above, water exists in the atmosphere in gaseous form, its liquid form either as water droplets in clouds or as rain, and its solid form as ice crystal in clouds, snowflakes, or hail, occur only momentarily and locally. Water vapor performs two major functions. It is important to the radiation balance of Earth as its presence keep the planetary surface warmer than would otherwise be the case. And second, it is the principal phase of the ascending part of the water cycle. The mass of water vapor in the atmosphere, which represents only 0.001% of the hydrosphere, is highest in the tropics and decreases towards the pole. At a mean temperature of Earth's surface of 15 degrees centigrade, the partial pressure of water vapor of at equilibrium with pure water is 0.017 atmosphere. The addition of salt to pure water lowers its vapor pressure. The equilibrium or saturation water vapor pressure of a saturated solution of sodium chloride is 22% lower than that of pure water. Precipitate water vapor has, on the average, a vapor pressure of 0.0025 atmosphere, which amounts to 15% of the saturation vapor pressure. The ratio of observed water vapor pressure to the saturation vapor pressure at the same temperature is the relative humidity of the air, and thus the mean relative humidity of the atmosphere is only 15%, a value that is low in human terms, in which level of 50 to 60% are preferred for maximum comfort. The relative humidity of the air, however, varies greatly from one geographic region to another and also vertically in the atmosphere. Atmospheric water vapor decreases rapidly with increasing altitude relative to its surface value. The amount of water required to surface a volume of air depends on the temperature of the air. At a high temperature can hold more water vapor at saturation than can air at low temperature, because the temperature of the lower atmosphere decreases rapidly with increasing altitude to about 15 km. The upper level of the troposphere contain little water vapor. Most of the vapor is found within a few kilometers of Earth's surface. The average relative humidity of troposphere air is about 50%. Above 15 kilometer, water vapor is essentially frozen out of the atmosphere, amounting to less than 0.1% of its concentrations at Earth's surface. Aside from temperature, other factors determine the water vapor content of the air and are particularly important in the lower troposphere. These factors include local evaporation and the horizontal atmospheric transportation of moisture, which varies with altitude, latitude, season, and topography. During a period of 10 days, that is the residence time of water in the atmosphere, Horizontal eddy turbulence may disperse vapor over distance up to 1000 km. When a mass of air at Earth's surface is exposed to a body of water, it gains water by evaporation or loses water by precipitation, depending on its relative humidity. If the air is unsaturated with a relative humidity of less than 100%, it gains water vapor because the rate of evaporation exceeds the rate of condensation. If the air is supersaturated within a relative humidity greater than 100%, the air mass loses water vapor because the rate of precipitation exceeds that of evaporation. This interaction between air masses and surface water bodies drives the atmosphere towards a state of saturation, which is not achieved for the entire atmosphere because of the variability in weather and because not all air masses are in contact with water bodies. In general, the level of atmospheric water vapor is higher in the summer since temperatures are higher at this time of year. Also, atmospheric water vapor content is higher near the source of moisture than in distant regions. Over the ocean, the air is almost always near saturation, whereas over the desert, where the supply of moisture is limited, the air is far below water vapor saturation value. In most cases, atmospheric water vapor content decreases inland over continents, but this decreases in is modified by rainfall condition, by the presence or absence of high mountains, large lakes, extensive forest, swamps, and by prevailing wind direction. Horizontal winds and air masses movement transfer water vapor from the ocean to the land. Although the processes are not completely separable, the horizontal transfer of water vapor seldom causes the vapor to undergo condensation, whereas vertical movement are most important in the condensation processes. Condensation depends strongly on the average temperature of Earth's surface because the water vapor content of the air is strongly dependent on temperature. In figure that show the states of water as a function of the variables of pressure and temperature. The slope of the phase boundary between liquid water and water vapor is positive, implying that with increasing temperature, the air at equilibrium will hold increasing amount of water vapor. Cooling or mixing of this air results in condensation of the vapor and precipitation as water droplets or as ice crystals. If the air temperature is below 0 degree centigrade, when first formed, the water droplets or ice crystals are very small, on the order of 10 raised to minus 2 to 10 raised to minus 3 centimeter in diameter, and they float freely in the atmosphere in large quantities. These water droplets and ice crystals produce a cloud. All clouds are formed as a result of cooling below the dew point. The temperature at which condensation begins when air is cooled at constant pressure and constant water vapor content. When the droplets or crystals coalesces to a size of about 10 raised to minus 2 centimeter in diameter, they become heavy enough to fall as raindrops or snowflakes. Hailstones measures about 10 raised to minus 1 centimeter in diameter or much larger. Water vapor condensing in the atmosphere contains strongly soluble salts, weakly soluble or insoluble solids, dust, and dissolved gases. The dust and sea salt aerosol particles in the air may act as sites of condensation by serving as nuclei for bringing initially a few water molecules together and including condensation from supersaturated air. Distribution of precipitation. Precipitation falling towards Earth's surface may suffer several fates. It may be evaporated during its fall or after it reaches the ground surface. If the surface is covered with dense vegetation, much of the precipitation may be held on leaves and plant limbs and stems. This process is termed interception and may result in the little water reaching the ground because the water may be directly evaporated from plant surface back into the atmosphere. If precipitation reaches the ground in the form of snow, it may remain there for some time. On the other hand, if precipitation fall as rain, it may evaporate, infiltrate the soil, be detained in a small catchment area, or become overland flow, a form of runoff. Overland flow, that is R, may be expressed in terms of intensity units, water depth per unit of time, as in equation 7. R is equal to P minus I, where P is precipitation rate and I is infiltration rate. Infiltration rate will equal precipitation rate until the limit of the infiltration rate or infiltration capacity is reached. Soil infiltration rates are usually high at the beginning of a rain, proceeds by a dry spell and decreases as the rainfall continues. This change in the rate is due to the clogging of soil pores by particles brought from above by the filtering rain and to the swelling of colloidal soil particles as they absorb water. Thus, rapid decreases in infiltration rate during a rain are more likely to occur in clay rich soils than in sandy soils. Between rainfall periods, water held in the soil as moisture is gradually lost by direct evaporation or by withdrawal by plants. Evaporation into the open atmosphere occurs at the surface of the soil and the soil dries progressively downwards with time. Water vapor in the soil diffuses upward, replacing the evaporated water and in turn is evaporated. The pumping of air into and out of the soil by atmospheric pressure changes and hence says the movement of soil moisture upward. It has been shown that evaporation of a water droplet in the free atmosphere and to a first approximation in various soiled atmosphere is proportional to the droplet surface area 4 pi r square. The diffusion flux of water at the droplet surface and the transfer of heat as the droplet evaporates. The equation rate for the rate of shrinkage of water droplets due to evaporation is dr upon dt dp sp minus 1 upon rp 1 plus x. Eighth equation, where dr upon dt is the rate of change in the radius of the water droplets. D is the diffusion coefficient of water vapor in air, and P is the equilibrium vapor concentration of the droplet surface. Sp is the degree of undersaturation of water vapor in the environment, and the P is the density of liquid water. X is a dimensionless parameter depending on dP, temperature, the heat of evaporation of water vapor, the coefficient of thermal conductivity of air, and the spherical coordinate system necessary to define process occurring to a spherical water droplets. Water droplets shrink when dr dt is smaller than 0, evaporates when the water vapor concentration in the environment is less than the saturation water vapor concentration at the droplet surface. They grow when dr dt is greater than 0, condenses when the converse is true in the free atmosphere. The term drdt has negative values for evaporation and positive ones for condensation. Use of this equation shows as an example that it would take 23 minutes for a water droplet to shrink, that is evaporate, in size from 50 to 5 micrometer, and a water vapor under saturation of 1%. Beside simple evaporation of water from soil, water is also returned to the atmosphere by transpiration in plants. Plants draw water from soil moisture through their vast network of root hairs and rootlets. This water is carried upward through the plant trunk and branches into the leaves, where it is discharged as water vapor. The term evapotranspiration is used in climatic and hydrologic studies to include the combined water loss from Earth's surface resulting from evaporation and transpiration. The maximum possible evapotranspiration is termed potential evapotranspiration and is governed by the available heat energy. It is taken as equal to evaporation from a large water surface and is generally much less than actual evapotranspiration. Actual evapotranspiration is never greater than precipitation except on irrigated land because of percolation of water into groundwater bodies and surface runoff. The soil moisture zone gains water by precipitation and infiltration and loses water by evapotranspiration, overland flow, and percolation of water downward due to gravity into the groundwater zone. The contact between the groundwater zone, phreatic zone, and the overlying unsaturated zone, Water's zone, is called the groundwater table. The water balance equation for change of moisture storage in a soil is given as S is equal to P minus E minus R, ninth equation, where S is storage, P is precipitation, E is evaporation, and R is surface runoff plus percolation rate into the groundwater zone. All terms are in units of length per unit of time. In humid mid-latitude climate, where a strong contrast between winter and summer temperature exists, there is an annual cycle of the water content of soils. The annual cycle of moisture is in soil in Ohio, US, for example, demonstrate for processing controlling the moisture, soil moisture. Of spherical special importance is that the soil are saturated in the temperature climate in the spring, and the evaporation rate is low because of the low input of radiant energy from the sun. By contrast, in the summer, evaporation increases because of the increasing solar radiation, and with the growth of plants, so does transpiration. Soil moisture is reduced to very low level at this time of the year. Thanks.